So we're pressing through Chapter 1. Did I mention already that a lot of faculty who teach Thermo 1 say, Monteufel, you're wasting your time covering Chapter 1? It's all prerequisite material. They're all 3,000 level. They know it all. Just press forward into the material. But I'll often find that it's in the prerequisites or in the past information, even in Thermo 2, that's you just didn't, yes, you were exposed to it, but you didn't just dominate it. You don't have 100% recall of that information. So I encourage you, if a lot of this is old school, you've seen it before, great. Just try to step it up, try to really bring it to the forefront so you can master it. Hydrostatics, rho GH. Rho GH. Have you been exposed to rho GH? Where if I have a vat or a tank of fluid and I want to know the pressure in the fluid, starting at gauge pressure of 0 pressure at the top, then as we go deeper into the fluid, the pressure on this wall increases with depth. So depth is measured by the parameter h from the free surface, and the pressure that depth is the density of the fluid, G times H. True? Make sense? Seen it? Manometer. So we covered barometers last time, but now we want to talk about a manometer. Here is maybe I have a pipe over here that's filled with air, or tank, and I want to measure the pressure in this tank. Well, I would connect it to a tube that is shaped as shown, and then I could leave this out to the atmosphere, or I could connect it to another tank or another pipe or another tube, P2. And the key part is that the manometer is that U-shaped portion. And maybe we fill it with some mercury. Maybe the mercury is like this, all right, such that the fluid level is the same both on the right side of the manometer as well as the left side of the manometer. The two fluids are at the same level. Okay, I know that I have some other fluid up here, but let's consider this as air. And because air is so dense, and maybe my fluid is mercury, Hg is so dense that the air is light, the mercury is dense, I neglect hydrostatics, the rho GH in the air, and I just say that the pressure right here at the top of the manometer on the left side is the same as the pressure where I want to sense the pressure at P1. It's the same pressure. And so this pressure right there is P1, and then the pressure at the top surface of the fluid, like the mercury in the manometer on the right side, that's the pressure P2. Okay, so if it's level, what can I conclude about the difference between P1 and P2? They're the same. There is no difference. True? So I then change up the problem. Let me redraw the problem. I'll try and redraw it quickly. So let's kind of go like this. And I have the mercury now in there, and the mercury level is on one side lower than on the other side. So the mercury level on the left is lower than on the right. Do not call this out. First clicker question of the day. For the system as shown, I'm interested in making an observation about the pressure P1 versus the pressure P2. So for this system as shown, answer A, this is a clicker question, I can conclude that P1 is greater than P2. Or answer B, no, I can conclude that P1 is equal to P2. Or answer C, P1 is less than P2. I will start collecting your responses, and we'll give you 30 seconds. I have a manometer. Air is the gas above the fluid, which is mercury in the manometer. Down to 5 seconds. Everybody in on 5? All right. So here's the result. So some people, most people would say that the air pressure P1 is greater than P2, right? That's what pushes down on the manometer on the left and pushes it up on the right. Let's kind of go through this logically. What is the pressure in the gas right above the fluid, the mercury, right at that point right here? Isn't that P1? Okay. And now, if I walk down and I go lower, 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 lower on the left-hand side till I get to the bottom of the manometer, what's happening to the pressure of the mercury as I'm going lower and lower and lower on that left-hand side? Isn't it increasing? Yeah. If then I think about going up, 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 up until I get to this point right here, which is at the same elevation as the left-hand side interface. Let's just say this is, I don't know, call it point B. What's the pressure at point B compared to the pressure at 1? They're equal. There's a little logic in that. Hopefully you followed it, okay? Kind of went down the same amount and up the same amount. Both sides are filled with mercury. So I'm at that level right there. So now I think about continuing the process going up, 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 till I get to this point, which we already know is the pressure at point 2. So what happens as I go up, 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 up? What's the pressure doing as I'm going up from B? Is it increasing or decreasing with respect to B? Decreasing. So what you could do is you could say, I don't know, let's say the pressure at 1 is equal to the pressure at the point B, true? And you could also say that the pressure at point B is the pressure at 2 plus rho of the fluid that's in that manometer, the mercury, the dense fluid that's trapped in the bottom, times G times the height difference between the two sides. So this concludes that, the pressure at 1 is not only equal, it's not equal to pressure at 2, but it's equal to the pressure at 2 plus some more due to the rho GH. Now, I know I explained that. I'm sure everybody in this room has seen a manometer problem, has probably solved them in homework as well as maybe even on exams. And then you're going to take fluids, and guess what? We start out with fluid statics before we get to fluid dynamics. Fluid statics is basically things don't move, manometer problems. But I encouraged the other class when I was lecturing this morning is don't guess. A lot of students, I think, are addicted to guessing. It's like, man, I know it's rho GH. Is it plus or minus? I don't know. I ain't got time. I'll guess a sign and move on. Let's get some partial credit here. This summer I taught fluids. I said this problem, like problem 3 on the final exam, is a manometer problem. When I was handing out the final exam, I said, no prisoners, so to speak. You know what I mean? It's all or nothing. You get it right or you don't get it right. I know it's rho GH. You get the sign right, you get full credit. You mess up a sign, zip. Okay? So think about that. Don't guess at that. It's really easy. It really is easy, but think through the process on your own. All right. So how do we grade this? Congratulations to the 91%. Gauge pressure. A lot of people have tires on their automobiles, tires on their bicycles, tires on their motorcycles, whatever, and you keep them inflated. They're a pneumatic tire that's air pressure, and so you have a gauge typically used. Here's a little digital display for a gauge in my pocket. I have a traditional pencil-type tire pressure gauge. I'm going to pass it around in a minute. Before I do talk about how this device works, let's talk about the nominal pressure in most passenger vehicle tires. Most tires, you need around 28, 30 psi. True? If you have a low-profile sports car type tire, they're different. Somebody said they put in 36 psi in that tire. Anybody own one of those really low profile? What do you put in? Do you know? 32? 35, a little higher. 42. Okay, so you have to know how many people have like a big SUV or a big heavy pickup truck and they have higher, what's the pressure in some of those tires? About 42. Anybody else? 50. How many people ever been in a semi, see a semi on a road? You see the truckers get out, they have a little baton like a baseball bat, they walk around tapping the tires. They're looking for low pressure when they tap them at the truck stops. You ever seen that? What's the pressure in a semi tire? 80, 100 psi. It's high. It's high, okay? So this pressure right here, this is a little hint. This is a gauge. That's a gauge to measure the pressure. Is that absolute 30 psi or gauge pressure? Gauge pressure. It's gauge pressure. So what is roughly the psi of the atmospheric pressure outside, the atmospheric pressure in this room, the atmospheric pressure you're going to breathe hopefully your entire life? So, yeah, what is 1 atm in psi? 14.7. Let's round it off to 2 significant digits to make math easy. 15 psi. So 15 psi is 1 atm, roughly. All right. So what is the air pressure, not in gauge, but the absolute air pressure for the air in your tire reported in units of psi? I could ask a clicker question. I would say answer A, it's 15. Answer B, it's 30. Or answer C, it's 45. Let's do it. We're going to have fun. I want to know the absolute pressure of the air in that tire when you put a gauge on there and it says it's 30 psi. Is it 15 psi absolute? 30 psi absolute? You don't have much time. You got to click in your answer. You got 10 seconds. Hopefully everybody got an answer in. Maybe it's didn't give you enough time. That's got to be it. You didn't like that question? What's the question? What is the absolute pressure of the air in the tire? It's 30 psi with respect to the gauge. Because the gauge goes, pushes out, oh, it's 30 psi in there. But that's a gauge pressure. And so the absolute pressure, think about that illustration we showed last time. We're measuring pressure from 0. If you measure it from 0 absolute, it's absolute up. You also have atmospheric pressure. If you measure up from there, it's gauge. What's the difference? Well, this is about 15 psi. So if you added, you said this was 30 psi gauge. What's the total pressure? 45 psi. A lot of times what they'll do, I think D was very confusing. D is a protest vote.
No, you look just like a D for me, so that's why I pressed it.
Oh, I'm sorry. Sorry. A, I try not to skip a letter in my choices. So a lot of times what we'll have is PSIG for an emphasis. We'll say PSIG, this is my gauge pressure in PSI, or I'll say PSIA, absolute. So there's less confusion in what pressure units we're reporting, or what's the pressure. So if a tire has 30 PSIG in it, it has 45 PSIA in it. How does this pencil-like tire pressure gauge work? Well, just like you probably broke a lot of toys after Christmas because you wanted to see how those toys worked, hence you're a good aspiring mechanical engineering student even at the age of, 5 or 6, is you take things apart. You break them to see how they work, and you look inside. And so this one luckily comes apart. A lot of them don't come apart, they glue them, but this one, I don't know, I got it apart. And so in the front part, the cap part, you put this up and you put in the stem. And right in that region there's a little rubber seal. Actually, it's now gone. There was one at the 9 o'clock. It's now gone. I'll pass this around. And it's supposed to seal it. And in the middle, the shiny part depresses the valve to let some of the air out of the tire and into the gauge. And there's typically a little hole, a little indentation right here to then let the pressure go back through a little hole into the system. But it's supposed to seal on that rubber going around. And if you don't put it on flat onto your valve, it'll leak a little bit, cock a little bit. You got to get it to seal. All right. Otherwise, it'll be leaking. Some of that air pressure goes in, and it feels right there is a black rubber type of piston, a plunger. And that piston there, right here, has a little indentation such that it forces the lip out against the wall of your pencil-like cylinder. And you know what? Somebody broke my plunger too from this morning. I'm going to pass it around anyway, but it's all broke up. Last time I passed around last year a thermometer and a wet bulb and a dry bulb, 2 thermometers, one came back broken. I don't know what happened to it, but anyway, the plunger then doesn't let air past it, but it has the same pressure as what's in the tire. Now, it's connected to a spring, and so that spring compresses as the plunger tries to move further down. Hence, if you have higher pressure, the plunger goes further, the spring is compressed more, and from Hooke's law, the force in the spring is the stiffness of the spring times the compression of the spring. It's held rigidly at this location. It's not able to go out. The spring is at the end of it. So what happens is you have the area, the force, you get the pressure, and so by having a calibrated stem, the stem also is sitting here on the connected to the plunger, and the stem gets pushed out. There's a little reddish type of cap of plastic that adds a little bit of friction such that when you take it off the tire, the spring will go back to its unelongated length, but it's not going to pull in your meter. It's going to stay out. That's why you measure it, you pull it up, you read it, then you push it back in to reset. They take another measurement on the second or third tire as you go around the vehicle. So that's for a little bit of friction, but it's not to stop it from being pushed out. It's just being so that I have to actually physically push it in to reset it. So that's easy, isn't it? Pretty straightforward. So, how much do these cost? $1, $2, $3. Somebody this morning said you can get a free discount tire. Somebody said yes?
The cheaper ones, though, they don't have the spring.
How do they work?
They just pop out and they stay there.
Well, no, that'll stay there too. You have to push it back in, but I would say buy one. They're all over the place. And if you're buying a set of tires from a place, ask for a free gauge. I know that a lot of places, probably I've seen places where people pull in and they tip the guy more than it costs for a tire gauge to check the pressure all the way around. And I think for those low profile, high performance tires, the pressure is more critical, isn't it? You just got to get that pressure right, otherwise you're just going to ruin the tire. So that's how tire pressure gauge works. Now on this one, I tried to take some picture. There's 2 sides to that stem that comes out, and there's 2 letters here and 2 letters here. So on this side, can you read the 2 letters? What are the 2 letters? LB. What are the 2 letters? KG. This looks like some U.S. customary system of units. This looks like some SI customary system of units, okay? Well, that's LB, so it looks like 10 pounds, 20 pounds, 30 pounds. Pressure in pounds? Well, they didn't have enough room to put PSI, so they just put LB. But if you go in there, it's kind of slang. You got to know the slang, right? Somebody says, how much pressure do you want in your tires? Oh, put in 30 pounds. What does that mean? They want 30 PSI. 30 PSI. Okay, so that's what that means. But on the other side, KG. What's that stand for? Kilogram. All right, put any kilograms in my tire. That makes no sense at all. Put in so many kilos. That don't make any sense. So is it kilogram per inch squared? Just like this was pounds per inch squared? No, that's probably SI. What would be, instead of an inch squared, what do you think is implied? Centimeters squared. Kilograms per centimeter squared. I took physics. I still remember this. I mastered it. I was an A student. This is great. I went and did a project where I put in some gauges in my car to read the voltage, to read the oil pressure or something. And this gauge I bought when I was about 18 or 19 years old had two sets of units, PSI, and then kind of red on the inner circle on this gauge, it had kilogram per centimeter squared. I said, that's not a good unit of pressure. Something's really wrong. My physics textbook never had kilogram per centimeter squared as a unit of pressure. But how many people have seen it? Some people have, from the response I got. Kilogram, I learned, is a unit of mass. Mass per unit area is not a pressure. Right? But it's just like this. Who's from Mexico or some country where they're all SI, right? Their mind doesn't work in feet, and it doesn't work in pounds. It works in kilos and centimeters. Whose mind works in kilos and centimeters and that? Okay. I ask you a question. What's your weight? Every student that I ask, what do they come back with? They say, oh, I'm struggling. I'm about 60 kilos, right? Not one student has ever told me, I'm so many newtons. Not one student has ever told me I'm so many newtons. Right? But what is the pure unit for weight in SI? Newtons. Kilo is a mass. Kilogram is a mass. So basically, sometimes you'll see a kilogram F. What? Well, it's just like what in the US. Sometimes you say, I want to buy 10 pounds of something. What? Well, are you buying 10-pound mass or 10-pound weight of that same thing? It really doesn't matter. 1 pound mass has a weight of 1 pound force at the Earth's surface. Most of us are going to spend our entire life at the Earth's surface. And then 6 foot under. Right? So a lot of times you'll see LBF and LBM because they add the clarifier. I want you to consider this pound force. I want you to consider this pound mass. Okay? That's what we're talking about. So sometimes you'll see this kg. I've never seen kgm. Never. But every now and then I've seen kgf. Meaning I'm talking about my weight as the kilogram force. Okay? It's the weight of a kilogram at the surface of the Earth. So sometimes you'll put kgf per centimeter squared. That's a good unit of pressure. You could go to other sites on the internet. They can do a lot better job of showing you how a tire pressure gauge works with that spring and little indicator in this end and that end. It's probably a lot better write-up than I can do. There's another tire pressure gauge. It's hooked up the same way. After you're done making the measurement, you push a little button to relieve the pressure. But this gauge doesn't have a little protrusion sticking out the end. It has a little dial where it starts to move. And it goes that way. True? This little dial indicator. How does that work? How does that work? Inside is a tube. A C-shaped, typically a C-shaped tube. They could have different shapes to them, but a lot of them are C-shaped. It's a Bourdon tube named after this French engineer who lived a long time ago. It's a Bourdon type tube, type of manual, non-electric pressure gauge. Right here, I have one. I'm going to pass it around. You could just take the plastic cover off, This is for refrigerant applications. So you would hook up the hose and you'd put the refrigerant and you'd sense the pressure of the refrigerant there. But I could take it apart, pull it out, take the back case off. And what do I have? A C-shaped. Let me see if I can do this with the dot camera, because there's so many students. What do I have? C-shaped Borden tube. And so what happens is it's connected through the linkages, and if you take your fingers and just bend it just a little bit, can you see the action? And then over here, you can see the action. Now, this thing has been passed around before, and it is so messed up. But I pass it around again, okay? But it's kind of neat to play with it. So everything in the world is not going digital, only 99.9% of it is. But that's very mechanical, okay? And so we should know a little bit. You can have electric power failure and your gauges would still work, okay, if it was this gauge. So what happens is the fluid is exposed down here. It can come up inside of this inside. It goes inside this tube. Now that tube is shaped a particular way. And when the pressure goes up, the tube tries to straighten out. And when it tries to straighten out, it pulls on this linkage through another linkage, and it moves the pointer. It moves the pointer. Sometimes you'll see a liquid inside the gauge, maybe an oil, and that's because it maybe is that gauge is put in a high vibration area, and it's always shaking. And so but you want a steady measurement, otherwise the needle would bounce all over. A lot of times they have a range. This gauge, what's the maximum pressure? 2,000. Just like that gauge that I'm passing around, some probably muscle man grabbed it and said, let's see if I can spin it around 3 times. Well, guess what? That gauge is worthless. It was worthless before I used it as a demo. But do not put on 4,000 or 6,000 onto this gauge. The gauge is going to be kaput. Something's going to bend or break in there, okay? All right. So that's one thing about these gauges. Respect their pressure range. What do we have here? We have 2 rings. We have an inner ring of red color showing you unit of PSI, and an outer black ring showing you unit of, hey, our new favorite unit of pressure measurement, kilogram per centimeter squared. Now the PSI, we said 1 ATM is around 15 PSI. 1 kilogram per centimeter squared is around 1 bar. It's around 1 atmosphere. So 1 to 1 for that one. So 1 kilogram force per centimeter squared is right at 1 atmosphere. It's not perfectly on, just like 15 PSI is not perfectly 1 ATM. Okay? But it's close enough. Here's some other gauges just to show you. What is this one? This one's actually made out to measure oil. Oil, it looks like it's good to measure between 20 to 80. Leave the ends alone. You know, typically the first 5%, the last 5% are not good on a gauge to be accurate. But here's another one. This one's a compound gauge. So what's happening? Well, here is 0. You can see it written right there. And as we go this way around, you're measuring kilopascal as well as PSI, so you can see it going up. You can see that 15 PSI is about 100 kilopascal, right? Okay. But what happens if you rotate this way? What are they measuring? VAC. It's a compound gauge indicating you can measure vacuum as well as positive pressure. What units do they use in in black for vacuum measurements? Inches of mercury. And so 1 ATM is around 29.92 inches of mercury, 30 inches of mercury. Notice they have negative kilopascal. And so about a negative 100, 1 ATM. Here's another one. Oh, look at that. Kilogram per centimeter squared. So it's more prevalent than you might think, that unit of measurement for pressure. How many units of temperature do we have? You can live your whole life and just use degree C, degree F, Kelvin, and very rare R. This is rare. I mean, it's not, these are very common. All right.
What is R used for?
It's the absolute in the U.S. customary system units. Now, what about pressure? There's a maximum of 4. Look at any physics book. Look at any chemistry book. Look at any engineering book. You're just not going to find 5, 6, 8, 10 measures of temperature. You're going to find 4. But what about pressure? Pascal, kilopascal, megapascal, bar, millibar, ATM, inches of mercury where the mercury density is 0 degrees C. Inches of water where the density of the water is at 4 degrees C. Torr, PSI-A, PSI-G, kilogram force per centimeter squared. Centimeters of water at 4 degrees C, centimeters of mercury at 0 degrees C, inches of water. It goes on and on. This is not an exhaustive list. There's more than 4. Pressure often is where a lot of students will make unit conversion problems. So please start to get very familiar so you can avoid errors on exams as well as in practice with pressure. All right. In the appendices, if you notice at the top of the steam tables, right up where they're giving you pressure, they give you the unit conversions for pressure. They don't really do it for temperature, but that just indicates it's an error-prone area. And so the textbook has added that to the table. Stevin's principle, you've probably not heard the name Stevin, but what it is it says at a fluid at rest, the fluid's at rest, the pressure depends on the depth from the free surface. It really doesn't depend on the shape of the container or the boundaries. So if I take a look at point A and B and C, they have the same depth from the free surface, but A is located where the surface of the wall is vertical. This one, there's some slope, and this one's some concavity. But they all have the same pressure. It really doesn't matter about the shape of the wall, right where that is measured from. Likewise, D and E are at the same location. This one, the surface is horizontal. This one is sloping, but they have the same pressure. That'll throw students for a loop. Hopefully everybody's shooting to not only get a degree, but maybe get on to the route to become a licensed professional engineer, registered professional engineer, which first thing you have to do is get a degree from an ABET accredited institution. You're at the right place. And then pass the FE exams so that you can become an EIT in engineering training. Then go and work for 5, 6 years, and then go back, document it, pay more money, sit for another exam for the PE exam. So the FE exam is critical. You need to pass that. Not everybody that takes it passes, even though you have a 4-year accredited engineering degree, from ABET accredited program. But one of the things, and I've seen it on multiple of these study guides and as well as exams, is they'll try to test that, and they'll say, what about the pressure at A versus the pressure at B? And the student will look and say, oh no, there's something different about the surface at A and the solid surface that's bounding the fluid at B. There must be a different pressure there. And they only give you like 2 minutes for every question on the FE exam. You got to be able to read it quickly, look at it, and know the answer and move on. Okay? It's a very simple exam. I don't know why there's not 100% pass rate even from UTSA grads. It's a minimum standards exam. But that just shows that you can shop instructors and not get a lot out of the tests and the exams and pass classes and still, that's the truth. So do you feel my encouragement? Get as most out of your class as possible. Every lecture. Pascal's principle. You probably heard of Pascal. So what is it? A pressure of a confined fluid. If you increase that pressure one place, that increase of pressure is felt throughout the whole confined fluid. So This is key in hydraulics, and there's a lot of machinery. Mechanical engineers do a lot with hydraulics. It's pretty simple once you understand it, but it heavily uses Pascal's principle. The key, one example is you put a piston over here, and below that piston is a fluid, a hydraulic fluid. It's connected to a hose from maybe a long way away, to another piston in a cylinder. And so, neglecting elevation changes, if I boost the force pushing down on this area of that piston, it will increase the pressure of the fluid right below it by that force per unit area, F1A1. That change in pressure will be felt below the larger piston, even if it's a long way away, because it's a confined fluid. Pascal's principle. Hence, I'm going to need a much larger force 2 to hold that other piston down, because my area 2 is much greater than A1. Or in other words, if I push down on F1, or area 1 with F1, I can lift something very heavy over there. And that's the beauty of hydraulics. For this to be in equilibrium, you have a new mechanical advantage. F2 can be much greater than F1 through that through the ratio of areas because of Pascal's principle. So it's used to transmit forces. Apply a big force over there by having a little force applied to the confined fluid over here. Yep, pallet jack, hydraulic bottle jacks, car jacks. Go to the shop where they lift your car, right? They lift it, and it's like, first time you see that, it's like, what? My whole car is just being lifted easily by little mechanics, just working a little toggle. It's all hydraulics. Front end loaders, all that equipment that uses hydraulics. Transmitting power. Archimedes' principle. You've heard of Pascal, you've heard of Archimedes, but what exactly is it? So if I have an object that's submerged, here's my object, it's submerged in a fluid. The net effect of being submerged in a fluid is to feel an upward directed buoyancy force. What is the magnitude of that buoyancy force? Well, it depends on the volume of the object that's submerged, and it's the weight of the fluid displaced by the object. So it's going to be rho of the fluid times g times the volume of the object that's doing the displacing. So that's the equation to give me the buoyancy force on a submerged object. It's the weight of the displaced fluid. A lot of people will think, oh, I need the density of the solid that's being submerged. In the equation, to calculate the buoyancy force using Archimedes' principle, is that rho sub F or rho sub solid? What is this rho right here? It's of the fluid. That means I could submerge, lead or silver or things that have different density, and it would have the same upward buoyancy force. It only depends on the density of the fluid that's displaced and the volume and the Earth's gravitational acceleration. Yeah, that's right. That's Archimedes' principle. You could even submerge a balloon filled with air. It's only that basically you're going to have to tether it. You're going to have to really hold it down. There'll be some tension in the wire holding it down if you're going to submerge a balloon filled with air. All right. This is part of the lecture you probably don't want to hear, but let me just encourage it, because when you get an exam back, a lot of students will go, well, I didn't solve the problem correctly, but he's really stingy on partial credit. Okay? Just there it is. It's for your good, because when you get to be 50-some years old, you don't like to hear of friends or colleagues or other people losing their job because they got only 50% of the calculation or design work correct and they messed up. And it has happened. It will continue to happen. So anyway, The strategy for getting correct answers is to be organized and neat. You already know that, but let me emphasize it. Clearly, I recommend a problem where you summarize what was given. You're given a problem statement, summarize that information. Repeat what is given to you. I had a teaching assistant just like Savannah and just like Emmanuel are helping this semester. But I really liked her. She was very good because she didn't take any crap off anybody. And she was just like, grow up. Get real. Come on. The people would just sit there and start, she'd give them a problem like they're going to be doing problem solving. And the students say, well, I don't know how to solve it, so I'm just going to wait for you to show me how. She didn't take any of that crap. She said, repeat what is given. Do that at least. Move. Don't just stand there deer in the headlights. Start to repeat what's known. Before you know it, it starts to put puzzle together. It's like, oh, this is what I know. I'm repeating the problem. That's a key to getting started. Clearly identify what you're asked to find. Am I asked to find the final temperature? Introduce a symbol with subscript. Am I asked to find the work? Am I asked to find the efficiency? And then think about what are the typical SI units. Is it going to be in degrees C? Is it going to be in kilojoule? Is it dimensionless? All those things help you get unstuck and start moving toward the solution. And then kind of go slow through the analysis. Maybe you say, I think I'm going to use some properties. I'm going to be using the first law. I'm going to introduce a control volume. I'm going to clearly identify my system. I'm going to assume it's an ideal gas. I'm going to use PV is equal to nRT. And then try to stay with symbols as long as possible. Resist the temptation, but when you do substitute numbers, substitute units as well. And check your units. Cancel your units. Be explicit with your units. And if you do all of those, you're doing well. You'll usually do okay. Significant digits. How many people have heard of significant digits before? All hands are up. Okay, these are one of these things where this may sound mean, but if you don't understand significant digits, you got to get it on your own, because me repeating it to you another time after another instructor before me and all through high school, etc., is not going to do you any good. You've got to learn things if you still have an uncertainty there. So, significant digits. Basically, we in engineering, just remember, 3 is kind of a magic number. 3 significant digits is useful. So I know that if you really studied and understand significant digits, a lot of times somebody will say, well, the temperature starts at 100 degrees C. And then they'll say, well, how many significant digits is that number? Well, purists could say, well, you only gave me 1 significant digit, unless you give me a decimal point. Now you've given me 3. Okay? That's okay, okay. Just assume that if somebody said the temperature is 540, that's 3 significant digits on the temperature. Or if they assume it's 1 megapascal, it's 3 significant digits on that, kind of as a baseline for your inputs, unless something really tells you that no, it's 100 degrees C plus or minus 20 degrees C or something. Really uncertain in your temperature coming in. But if most of the inputs are known to 3 significant digits or more, what's the maximum your output can be known to? 3. You can process all those through the calculation. The calculator spits out 8. Don't report 8. Did I mention you'll lose points on the exam? I'll take off points for over-specifying the number of significant digits you know an answer to. All right. So also box your answer. This is a declaration of your final calculation, right? So inside the box there should be a equal sign. If you don't have an equal sign inside the box, you have a problem. Because when you have a declaration of your final answer, you need to put on the left side what you were looking for. I'm looking to calculate the mass. I've now calculated it. Here it is. It's equal to. And on the right-hand side, you really often, almost always, have 2 parts. You have a numeric value with units. And if you leave off units, so this is bad news, right? They don't like to hear it. But you don't want to lose points, and you want to know up front. If I overspecify the final answer too many significant digits, I'm losing points. 3 and 4, you'll never lose points. 5, 6, 7, you'll always lose points. And if I fail to put a final answer in a box, I'll lose points. If I fail to put an equal sign with what I'm looking for, with units, I lose points. Got it? Then somebody else said, is this a box? No. What happens if I calculate it 2 ways, and I think they're not the same answer, but one has to be right, and I can't figure out which one's right. So what I'm going to do is I'm going to let you decide, instructor. It don't work that way, okay? It's been tried before. All right? Professor, you want the answer in a box? There's your box. No, no, no. One equal sign in the box. Not multiple lines and multiple equal signs. One. One equal sign. Something on the left, something on the right. Not a run-on box, okay?
What if it's a multiple part?
Then you put a little A. Then you come down, and then you have part B. And then you have another box. So, yes, you have a box for every part. Now, sometimes I'll have a table. Just put the answers in a table. So it's like 99% of the time it falls in a box. Sometimes it's a table. It doesn't fit in a box. All right, G. Does G change with elevation? If I go to 30,000 feet, I'm flying in an aircraft. I step on the bathroom scale. Did my weight change? Very, very, very little. Very little. Okay? It's so little that it's negligible. It doesn't really change with elevation. But here are G at a couple locations. Chicago, Illinois, Houston, Texas, San Antonio, Texas, Monterrey, Mexico, Mexico City, and Bogota, Colombia. Is G 9.81 the worldwide? It is not 9.81 the worldwide. Look at the numbers. How many digits are each of these given to? 5. Question, last clicker question for today. Of all these G's that are shown above, they all agree to either 4 significant digits, 3 significant digits, 2 significant figures, or significant digits, or 1. I use it pretty well interchangeably, significant figures or insignificant digits. I'll give you a little more time. What do they agree to? All right, so if you start rounding them off, if you say, I want this number to 4 significant digits, it would be 9.804. I want it to 3 significant digits, 9.80. If I want it to 2 significant digits, 9.8. And if I want it to 1 significant digit, basically 10, okay? So you do that for every one of these, and then you'll see that, you know what, this is 9.79, blah, blah, blah. But what do they really agree on? 9.8. This is 9.8, this is 9.8, this is 9.8, that's 9.8, etc. So they agree to... They agree to 2 significant digits. Thank you for your attention. We'll see you next time.